Hi everyone. This is approximate Earth mover's distance in truly subquadratic time. I'm Lorenzo Beretta from Copenhagen University, and this is a joint work with Aviad Rubinstein from Stanford. So what's Earth mover distance? Well, we are given two sets, A and B, of endpoints in a metric space, and we define the Earth mover distance between A and B as the minimum cost of a perfect bipartite matching between A and B, where the cost for each edge connecting two vertices is exactly their distance in the metric space. Usually, Earth mover distance is introduced in a more general fashion as a distance between probability distributions over metric spaces. And we can easily see that the definition that we gave is a special case where every point in the metric space has the same probability. And for our result, we just prove things for this like uniform case, the simpler case, and everything extends to the more general case. So for the sake of this talk, we just refer to the simpler case. So let's now see some applications of Earth mover distance. Earth mover distance is often referred to as optimal transport and has applications in machine learning because there are like differentiable algorithms to compute this optimal transport. It can be used as a loss function for deep learning, for example. It can be used in computer vision as a metric over images and also in NLP, natural language processing. And it's nicknamed Earth mover distance. So if we want to compute the distance between two passages, we just see a passage as a set of words, and the words can be embedded in a metric space by what's called a word embedding, usually some like deep learning machinery that like that maps words into vectors, and then we have like a metric space over words. And then we can compute the distance between two passages as the Earth mover distance between like these two set of words. And if they have like different cardinality, then I mean we just need to use the more general definition of Earth mover distance as a distance over probability distribution. So all in all, EMD is a very natural metric in data science, so it's worth studying from a theoretical point of view. So let me now give an outline of this talk. So in this talk, first we go on a tour of literature and study the complexity of Earth mover distance. And then we see we review a matching algorithm from the 80s, pretty old algorithm from Gabo and Tarjan. And then we see how to implement this algorithm in sublinear time to achieve our main result. That's going to be as the title says, a sublinear time algorithm for Earth mover distance on general metrics. So first, literature tour. Okay, so what if we want to solve Earth mover distance exactly? Then we have a almost linear time algorithm, yeah, that actually is like n to the 2 plus small o of 1. And this is a Chan et al. From Fox 2022, the mean cost flow in near linear time. And there is a lower bound that says that conditionally on SAT, no strictly subquadratic algorithm can compute Earth mover distance exactly. What about approximation? So if we consider a very important case, that is the Euclidean case, so instead of being on a general metric, we are in a Euclidean metric, then in low dimension, this problem is much easier. So if we want, we can get an approximation scheme, so 1 plus epsilon approximation in linear time in n. And here, when I say low dimension, I mean the constant dimension, and so the size of the input is essentially n. And Sharad Kumar and Agarwal in already STOC 2012 solved this problem. I mean, there's been like more work on that to like make the algorithm deterministic and so on. And what happens if we are in high dimension? Oh, sorry. So if we are in high dimension, then a very recent paper, Andoni and Zhang, Fox 2023, showed that we can achieve a 1 plus epsilon approximation with strictly subquadratic time. Although how subquadratic depends on the constant epsilon. So it's mainly like about breaking a barrier. And our result is like very similar in spirit to this one, because we're going to prove like that basically we can achieve an epsilon additive approximation with a running time that is basically the same as theirs, but we work on general metric, whereas they work in high dimension Euclidean space. So for general metrics, it's easy to see that no constant approximation can be achieved in strictly subquadratic time. Why? Imagine we have this metric space here on the left. Imagine for every pair of points, their distance is very large, extremely large. And then those points that are connected with a black line are closer, whereas the points connected with a green line can be as close as those connected by a black line or significantly further. So the Earth mover distance is determined by whether the green line means kind of as close as the black line or significantly further. And if they're like significantly further, then the Earth mover distance is going to be large. But if they're like as close as the black line, it's going to be small. So basically, the problem reduces to like finding this green line and like computing the distance. But you cannot do this in any like reasonable sublinear access model, right? Without inspecting n squared um, cells in your adjacency matrix or like cost matrix or distance matrix of this problem. So that's why we consider an additive approximation, because multiplicative approximation is not promising in this setting. We cannot, in general metrics, we cannot achieve any meaningful result with multiplicative approximation. So Earth mover distance has a long history of being studied in sublinear models, in the Euclidean setting, in streaming, and massive parallel computation under multiplicative approximation that doesn't really work for general metrics. So for general metrics, we show the first sublinear time result for general metrics. So what does sublinear mean for general metric? Well, if the problem is a general metric, then the input is an n times n matrix. So anything that is strictly subquadratic or like subquadratic is sublinear. So that's what we achieve. And as we saw, we have to achieve this through additive approximation because multiplicative approximation is not possible. So how do we compare with this latest work from Andoni and Zhang from Fox 2023? They solve the problem for Euclidean metric and they give a multiplicative approximation. So they do it in strictly subquadratic time, but for Euclidean metric, the data is represented with like n times d bits, where like d is the dimension. So this is not really sublinear. And the techniques they use are a combo of like they build like a spanner for the metric using LSH techniques, and then they solve Earth mover distance, like the matching problem, as a mean cost flow instance over the spanner. So if the spanner has strictly subquadratic size, by mean cost flow in near linear time, we get a strictly subquadratic algorithm for Earth mover distance. So that's more or less a gist of their work. So what is our result? Our result says that given two sets of size n and a cost function between 0 and 1, that honestly that doesn't need to be a metric. It can be an arbitrary cost function. And a constant epsilon greater than 0. In strictly subquadratic time, depending on epsilon, where the exponent depends on epsilon, we can return an approximate value for the Earth mover distance that is up to an additive constant epsilon far from the Earth mover distance between A and B. It's worth to notice that we do not return the whole matching, but just the cost. So what's called the EMD, the actual distance. So let's now review an algorithm from the 80s, because like the idea behind our contribution is that we take this algorithm from the 80s, we heavily inspired by this algorithm. We implement it basically in sublinear time. So let's first see this algorithm. So instead of like running this algorithm, we are heavily inspired by it because instead of like running this algorithm verbatim, we rather like solve an easier problem and use the same algorithm to solve an easier problem. And like this easier problem turns out like for this easier problem, we can implement the algorithm in sublinear time. So the problem is as follows. We get as input a cost matrix, the cost matrix like with values in between 0 and 1, and the constant gamma between 0 and 1. And what we want to output is a matching of size gamma n. And matching with outliers is stronger than an additive approximation because if we have a matching that is like that large, like of size at least gamma n, then we end up paying at most 1 minus gamma n if we just match the remaining vertices arbitrarily. So here we present an algorithm for maximum weighted perfect matching with outliers. For now, we just work, I mean, imagine we're working in a standard RAM model, so we're not doing anything sublinear. So you might be familiar with this linear program. It is a linear program for minimum perfect matching. So here we have a variable x u v for each pair of u in the set A, the left-hand side set, and v in the set B, right-hand side. And we want to minimize um, the basically the cost that we pay. And here you should think of like xuv as an indicator variable that is 1 if uv is included in our matching and 0 otherwise. So we're basically paying for our matching in our cost function on the primal side. And we enforce that every vertex is included in the matching, both on the left-hand side and on the right-hand side. And of course that these variables are non-negative. And the dual turns out to be a potential function. So each vertex is associated with a non-negative potential, and we require that the sum of potentials on the endpoints of an edge of cos CUV is at most CUV. So how do we solve this? How do we use this linear program to like get a good algorithm for our matching, minimum cost perfect matching with outliers? We use this like primal dual schema. It works as follows. So we maintain a pair m phi, where m is a matching and phi is a potential, so a primal dual pair. M is a partial matching, so it is not a perfect matching. And phi is a quasi-feasible dual. It means it doesn't quite satisfy the dual constraint, but almost. So phi u plus phi v is at most the cost of the edge uv plus 1. And for each edge in the matching, we have complementary slackness. So basically, we have equality. So phi u plus phi v is equal to the cost of that edge. We maintain all these invariants. And we grow m up until the size of m is large enough to satisfy our matching with outliers constraint. And then we can analyze that it is in some sense correct. So complementary slackness ensures that if we compute the combined cost of edges in our matching, then this is at most the combined potential, and the combined potential is in turn at most the sum of the cost of an optimal matching um, plus 1 because of the quasi-feasible condition. And this is like at most op plus n. Now this additive term n, if we like scale things correctly, we can basically hide this under the carpet of our additive approximation. But we don't want to like work all the details here, just give like a sense of why things work. So, sorry. Okay. Okay. So the first step, our goal is now to grow our matching M, satisfying these invariants. So the first step to grow our matching is the following. So we consider the tight edges, so the edges that satisfy the quasi feasible inequality tightly, so they have an equality sign there, and we grow m um, along augmenting paths of the form of this form, go through a tight edge, then they go back through an existing edge. So like the solid black edges here are the edges that are already included in M, and then forward again along a tight edge. So basically tight edge, tight edge, existing edge, and so on and so forth. So what does it mean that we grow M along an augmenting path? Well, it means that we basically uh, toggle this the edges along this augmenting path. So we do like an XOR. If an edge belongs to M and to the augmenting path, we remove it from M. And if an edge does not belong to M, then we add it to M. And we just take a maximal set of no disjoint augmenting paths of this kind, and we perform all this augmentation at the same time. And simultaneously, for each node on the left hand side that belongs to one of these augmenting paths, we decrease its potential by 1. Why we do this? Oh well, we do this because if an edge was tight before, then now we want it the same equality to hold, but without a +1, so that we satisfy our invariance. And the second step is meant to increase the number of tight edges. So the first step basically ensures that as long as there are tight edges, we're like growing our matching. But what if there are no tight edges? Then what we do, step 2, increase the number of tight edges. And to do that, we start like coloring in black the free vertices in A on the left hand side. And what we do is that we grow a forest rooted in this black vertices, and we grow along tight edges in one direction and existing edges in the reverse direction. And we color in gray all the vertices in the forest. And what we do is that we increase the potential of vertices on the left hand side of the forest, and we decrease the potential of the vertices on the right hand side of the forest. This once again ensures that the invariants are still satisfied and potentially unlocks more tight edges, because all these edges that have like one vertex in the forest on the left hand side and one vertex outside of the forest on the right hand side might become tight and might unlock more augmenting paths. Basically, this is the intuition behind it. So our algorithm basically alternates between these two steps. So growing along augmenting paths and increasing the number of tight edges through a forest that we grow. And the running time, it's not too hard to analyze, because here we assume that the cost function is bounded, is like an integer, bounded integer. All these assumptions, I mean, they're like kind of easy to work out. You can play around and up to like rescaling things and rounding things. You can assume that this holds. And after t steps, we have the free vertices on the left hand side. All of them have potential t because they're always in this forest. Whereas the free vertices on the right hand side, they have potential 0 because they are untouched. So if we just combine the cost of matching like these free vertices on the left hand side and free vertices on the right hand side arbitrarily, then since the cost is bounded, we get the inequality that the number of free vertices times t is less or equal than big O of n. Of course, this thanks to the feasibility of the potentials. So in turn, it means that if we only want the free vertices to be like a small fraction of like a small fraction of the total, that is what we want. We want like the free vertices to be, let's say, 1 minus gamma n for some gamma. Then we just need t to be a large constant. So how do we implement this algorithm in sublinear time? Well, first of all, as we said, we do not return the whole matching. So a key idea to this purpose is to define what a matching oracle is. So instead of returning a matching, we return a data structure, match M, that given a vertex U, it returns V if UV belongs to the matching, and otherwise it returns error if U is left unmatched. And this data structure is like fairly fast in that it runs in times n to the 1 plus epsilon. Now, once we have such data structure, then it's very easy to compute the cost of the matching. You just like sample edges from this data structure. So large maximum. So the way we build our algorithms, like we hinge heavily on a result, a recent result in literature from Bhattacharya, Kiss, and Saranurek, Fox 2023, and what they do in their paper is that they design this algorithm called find large matching. That what it does is that it finds a pretty large matching whenever there exists a large matching. So whenever there exists a matching of like linear size, so of size delta n for some constant delta, then they return a matching oracle for a matching that is also linear size. Of course, like it shrinks, is not as big as the one that is like promised to exist, but it's still linear size. And their algorithm runs in times n to 2 minus epsilon. So basically, their algorithm like finds pretty large matching in strictly subquadratic time. This is the contribution. And in a nutshell, we use like this fast matching algorithm to like build augmenting paths in parallel and build spanning forests in parallel and implement our two steps in sublinear time. Now, I won't get into all the nitty-gritty details of how we do this, but you are welcome to read the paper, and especially the technical overview explains all these details in a more understandable fashion. And thanks for listening.